Lecture 4.2, Wave Packets. In the last lecture, we discovered that all particles in nature can exhibit a wave-like nature under the right conditions. These particle waves are called de Broglie waves. De Broglie waves let us calculate the probability of finding a particle at different locations. We started out by looking at infinite traveling waves, and we characterized their motion using the wave number k, which is 2 pi over the wavelength, and the angular frequency omega, which is 2 pi times the frequency. We saw that the wave number encodes the momentum of the particle, and that the frequency tells us the energy of the particle. In today's lecture, we examine wave packets. A wave packet is a spatially localized wave. In other words, it is a wave that has a beginning and an end. Here's an example of a wave packet. If we put the wave in motion, we see that the wave crests move to the right, first growing in amplitude and then dying down as they move through the packet. This wave packet was formed by multiplying a traveling wave by a Gaussian envelope shown in red. The envelope is stationary as the wave crests move through it. We can define two velocities to characterize the motion of the wave packet. The first is the phase velocity. This is the velocity of a surfer riding on the local wave crests. In this example, the phase velocity is positive since the wave undulations are moving to the right. The second velocity is called the group velocity. It is the velocity of the envelope of the wave packet. In this example, the group velocity is 0 since the envelope is stationary. In general, the phase velocity can be less than, equal to, or greater than the group velocity depending on the underlying physics. Here's an example where the phase velocity is greater than the group velocity. In this case, the individual crests catch up to and overtake the packet envelope. And here's an example where the group velocity is greater than the phase velocity. Now it is the envelope that overtakes the individual wave crests. In a dispersive medium, the phase velocity varies as a function of the wave number k. The function omega sub k is called the dispersion relation for a particular medium and physical situation. Glass is an example of a dispersive medium. Light slows down when it passes through glass, with violet light slowing down the most and red light slowing down less. This is what causes prisms to separate light into monochromatic colors. Water waves also travel at different speeds depending on the wavelength or wave number of the waves. So water is also a dispersive medium. And finally, in a vacuum, light travels at the same speed c, and so therefore a vacuum is non-dispersive with respect to light waves. If the dispersion relation is known for a given physical situation, the phase and group velocities can be calculated. As we have seen before, the phase velocity is just the ratio of the angular frequency to the wave number k. The group velocity is the derivative of the angular frequency omega with respect to the wave number k. Let's now calculate the phase and group velocities of a de Broglie wave. The phase velocities we've just seen is the angular velocity over the wave number. If we substitute that the energy of a particle is h bar omega and its momentum is h bar k, we plug these in for omega and k, so omega is e over h bar and k is p over h bar. The h bars cancel, and we get that the phase velocity is just the energy of the particle divided by its momentum. We can now substitute relativistic equations for energy and momentum. So energy is gamma mc squared, and momentum is gamma mv. So if we plug those in for E and P, the gamma m's cancel out, and we get that the result, that the phase velocity is c squared over v. We can factor it out like this. So if we group a c with the v, we get quantity c over v, which is a dimensionless number times the speed of light. So this is a kind of a funny result because, velocity is always less than c, so c over v is always going to be a number greater than or equal to 1. So the phase velocity of a de Broglie wave is always greater than the speed of light. So remember from special relativity that physical particles can't go faster than the speed of light. Turns out information also can't go faster than the speed of light. So whatever the phase information of these de Broglie waves are, it can't be used to transmit information faster than the speed of light. We'll come back to this a little bit later on. Okay, let's now calculate the group velocity of a de Broglie wave. Remember that the group velocity is d omega dk. Again, we're going to use the relations E equals h bar omega and P equals h bar k. We'll differentiate these two expressions to get that dE equals h bar d omega and dP is h bar dk. So we can solve for d omega and dk and plug those in. The h bar factors are going to cancel out, and so we get that the group velocity is just dE dP. Let's use the classical limit that the total energy is just the kinetic energy is p squared over 2m. And now if we differentiate this expression, we're going to differentiate the kinetic energy with respect to momentum. For differentiating p squared with respect to p, you just get 2p over 2m here. The 2's cancel. If we plug in that the momentum is mass times velocity, now the masses cancel, and we find that the group velocity is just the velocity of the particle. So, very simple result. So we see that for these de Broglie waves, the group velocity of the wave is what is equivalent to the classical velocity of the particle. Okay, let's look at an example. Let's say that we could somehow measure the de Broglie wavelength of an electron, and we find that its de Broglie wavelength is 2 picometers. A picometer is 1/1000th of a nanometer, or 10 to the negative 12th meters. So if we have that information, we can calculate all this stuff from it. So we can find the momentum, kinetic energy, phase velocity, and group velocity just from that one measurement. So momentum is Planck's constant over the wavelength. If we multiply top and bottom by h, it's easier to calculate a value here. So remember, hc is 1240 electron volt nanometers. Since we know the wavelength, remember a picometer is 1/1000th of a nanometer. So if we use 1240 electron volt nanometers, lambda's got to be in nanometers. So it's going to be 2 times 10 to the negative third nanometers. Multiply that out, we get 0.62 MeV per C. So that would be the momentum of the electron. So the kinetic energy we can calculate from the total energy, and the total energy we can calculate from the momentum. So the total energy is given by the square root of Pc squared plus Mc squared squared. We just figured out what the momentum is, and the rest energy of the electron is 0.511 MeV, so these are both in MeVs. Plug in the values, you get 0.803 MeV. And so that's the total energy. The kinetic energy is the total energy minus the rest energy. So 0.803 MeVs is the total energy, subtract off the rest energy, and you get 0.292 MeVs. So that's the kinetic energy of the electron. The phase velocity, remember phase velocity we found to be c over v times the speed of light. So we need to find the velocity to find the phase velocity. And we can do that using E equals gamma mc squared. So we know we just found the total energy and we know the rest energy. So from E and mc squared we can find gamma, And from gamma, we can figure out the velocity. So let's plug in gamma here and then solve for v over c. So after a little algebra, we find that v over c is the square root of 1 minus mc squared over e. If we plug in our values for the rest energy and the total energy from the previous slide, we find that v over c is 0.771. So it's going at 77% the speed of light. Now that we have v over c, we can plug it in, find the phase velocity. So in fact, the phase velocity is just going to be the speed of light divided by 0.771, which turns out to be 1.3 times the speed of light. So it's going 30% faster than the speed of light, the phase velocity. All right, finally, the group velocity is very simple. Remember, the group velocity is just equal to the classical velocity of the particle, and we've already calculated that. We found that v was 0.771, so the group velocity is 0.771 c. Okay, so that's it for this example. In the next lecture, we will look at how to construct wave packets which describe particles.